Welcome back to CS479 machine learning for 3D data. Actually, I also just posted the link of these slides in the Slack, so you can also find the link in these slides. And I also realized I didn't post the link on the course webpage. I just, was added the link of the slides in the course webpage. So you will be able to see the link on the course webpage in a few minutes as well. Okay, so let's start. As I said multiple times in the previous lectures, our Zoom policy is that please set your name like this, and also please turn on your camera and turn off your mic. So that's the Zoom policy. And also the thing is that as I said like last time, so all the programming assignments are already released on the course webpage. And the due date of the first assignment is the next Sunday, the Sunday not in this week, but the Sunday at the end of the next week. And I strongly, if you did not basically have the setup, of the programming the things on the K-Cloud server, I strongly recommend you to complete to basically make the setup for the programming the environments the server and start to work on the first assignment. So we basically intended that you have at least like 2 weeks for each of the assignment. So from this week, you're having the 2 weeks for the first assignment, and another 2 weeks for the second assignment, and another 2 weeks for the third assignment. But since all the assignments are already released, you can start to work on all the assignments from now. But if you did not actually complete the programming environment setup, please do that as always possible. And if you have any issues with the K-Cloud, please let us know. And also, as I said in the previous lectures as well, we are also having some of the quizzes during the lectures. And answering these quizzes is actually really big part in the final grade. So if you do not answer at least like 80% of the quizzes, then you may not be able to get the full credit, full score for the participation. And this will really result in some downgrading in the final grade. Please participate all the quizzes during the lectures. And the most important thing is that actually, the course project is the most important part in this course. And we're gonna have some bunch of things in terms of the course project. And the first thing that you need to do is that you need to basically make a team for the project. So the deadline with the team matching is the September the 8th. You can also check out all the details about the team matching. So let me briefly share my screen with the course webpage things. So if you go to the course webpage, you can see all the details about the programming, the assignments, and also the projects as well. So in the project the tab, you can also find the team matching the page, and you can see all the details here. So what you need to do after making the team is that you need to make a submission to the open review the page. So if you also go to the open review page, let me open up. I didn't put the link here. But basically, you can find the link of the open review in our Slack, the workspace. And what you need to do is that you basically need to submit not only the names of the teammates, but also the project title and also the project keywords as well. So do not worry too much about the project title and the keywords. You can basically change all the idea for the project. But you basically need to form a team with at most 3 people. And the deadline for that is basically this Friday. So that's basically the thing. So just in case that you're having some difficulties, like finding some other teammates, you can also utilize the Slack, the workspace. So there is the project team matching the channel on this Slack. So you can utilize the channel to introduce yourself and also to find some other teammates. So we are basically asking you to basically register on the open review by the deadline as a team, not as kind of each of the single person. And you can find the link here, and also you can find the same link on the Slack workspace as well. Any questions for this? Any question on the team matching or the assignments? Okay. So let's briefly recap the things that we discussed last time. So we basically discussed last time some kind of the ideas about like how we're gonna represent the 3D data. So we basically have seen some bunch of kind of the representations for the 3D data. Obviously, the first idea might be basically having the 3D grid. As we have the pixels for the images, we can consider having the voxels for the 3D case. And obviously, the downside for this kind of the grid representation is that it will be basically very huge waste of the memory in terms of that most of the boxes might be empty. So we have seen last time, as we basically increase the resolution of the grid, we're gonna see actually that most of the boxes becomes empty. Then this might be very kind of the kind of the waste of the memory in terms of like basically representing this kind of 3D data with the lots of the voxels. The other way around to represent 3D data might be basically using the images. So basically, we can also consider rendering the 3D models into the multi-view the images, and basically aggregate all the information to process the data. So this kind of the representation basically can be good in the case that especially when you have some sort of the not only the geometry information but also some kind of the appearance information. For example, like when you have some kind of the color or the texture or some material information over the surface, then having this kind of like rendering of the 3D models into the images actually can be kind of useful. But actually, even for the boxes, we can also obviously utilize this kind of information as well. And also the thing is that even when we do not have this kind of appearance information, just having this kind of the some grayscale images might be still like sufficient to process the 3D data. And this actually the multiple representation is quite effective in most of the cases. The only downside is that if you want to get some kind of the good the accuracy in many kind of some prediction the tasks using the neural net, the thing is that you also need to have lots of images, not just having the single image, but you typically might need some many of the images to get the best accuracy, which means that it might also take some kind of the loss of the memory and also the computation time as well. So that can be kind of the downside. The other representation that we can typically see is also the point cloud. And the point cloud is basically the representation that we can basically see for many kind of some scan data. So basically we use some kind of 3D scanner. The output that we can typically see is this kind of the point cloud. And actually we're gonna also see some of the ideas in terms of how we're gonna process this kind of the point cloud data using the neural network. And you will basically also see that the architecture, like processing this like point cloud data is quite simple and also fast and also relatively easy to implement. So this might be kind of the good thing in terms of like utilizing this kind of like point cloud data. Obviously, the downside is that when we only have the point cloud, that means that we do not have any kind of surface for the topology information. But we can also see later in this lecture in terms of like how we can also recover this kind of surface information from the point cloud as well. But that basically means that we basically need to have this kind of like conversion step from the point cloud to some kind of surface representation. And also we basically have some weaker approximation to the power, which means that if you want to get some kind of the recover the details, the geometry information, we also need to have some loss of the points. So that can be downside. The other representation might be the mesh. So mesh is the kind of the most typical representation for many kind of some 3D CAD models. Many of the 3D models that we can see in many kind of the online repositories of the 3D assets. For those kind of the cases, like having the mesh is good in terms of that we have the surface and the topology information. And also having the mesh can be good for many kind of the applications like rendering and the manipulation and many other things. So that can be kind of good thing in terms of like utilizing the data in many applications. Obviously, the downside is that mesh does not provide any kind of some regular structure. So if we can, if we want to basically apply some kind of the typical the convolutional the operation of the mesh, that's not that kind of easy thing. So we also discussed some idea that how we can basically make some kind of some specialized some conversion the operation of the mesh, which is basically adding some lots of the engineering in the neural network architecture. So that's not that kind of easy thing. And also the thing is that there are kind of the many basically the constraints in terms of like defining the validity of the mesh. So if we, in the kind of perspective the generation, if you want to basically generate a mesh directly as the output from the neural net, there will be lots of the difficulties in terms of like satisfying all the constraints for the validity of the mesh. So that's the downside. And also there can be some more the complicated representation, especially for some CAD, some kind of things. So many the CAD applications, there are lots of the many other some more the complicated the representation that typically also not only encoding some geometry information, but also some structures as well. Like what are the kind of the parts with the sharp edges, and what are the parts that are symmetric to each other for those things. So having this kind of some structural representation can be good for many applications, but it also making some more kind of difficulties in the some kind of the processing the process. And so there are some kind of the works of like generating this kind of the some structured representation as the output of the neural net. But those are also kind of like very easy to very challenging to implement. So there are also lots of difficulties with generating all these kind of representations. So we basically compared mainly these four representations, especially in terms of like, so processing the perspective. So mesh can be good for many kind of the aspects in terms of like having some geometric fidelity, and also in terms of the efficiency, and also for many of the application, mesh can be good. The thing is that mesh is not kind of the best representation in terms of the generation and also the processing as well, because of the irregular structure of that. So in terms of the processing, the voxels and the multi-view representation can be good, but also in terms of like some applications for the rendering, the manipulation, voxels and the multi-view may not be the ideal the representation. So these are kind of the pros and the cons. And the point cloud can be good and bad for many kind of things. Still, the point cloud is not the ideal representation for many kind of the applications. And also it's not good for the processing as well, in terms of that it does not provide any kind of the regular structure. We're gonna get into the idea in terms of like how we can also handle the point cloud data for many kind of some processing the pipelines. Actually, we'll see that like some simple the idea in terms of processing the point cloud actually can be quite effective. So which means that the point cloud actually can be good for some many the processing the tasks, but still not for some kind of generation the tasks. So that's basically what we are going to discuss in the later lectures. And also the implicit representation was kind of another idea in terms of like representing the shape like in a kind of implicit way, which basically means that we are having a function that basically represents a 3D shape in terms of like if we provide any kind of query point in the space, the function is basically giving the information whether the point is in the inside or the outside of the 3D shape. So that can be another kind of way that we are representing the 3D shapes. The thing is that since now the shape is represented as a function, this can be the representation as the output with some neural networks, but that cannot be a kind of input to the neural net, because the function, the representation itself is kind of the function. So we can also get into this idea in terms of like how we can basically generate a 3D shape with the implicit representation. So previously, what we also discussed is that like when you have this kind of like multiple representation, how we can do some kind of the conversion from the one to the other. So what we have seen last time is that if we have some kind of the implicit representation, like converting that into the voxel is quite straightforward, because we just need to evaluate the function for each of the voxel, right? And also like generating the point cloud from the mesh is also very straightforward, because we can just like sample the points over the surface. So that's also quite easy kind of a task. Like generating the multi-view from the mesh would be also quite straightforward in terms of that we can just like render some, we can use some kind of rendering function in the graphics in terms of like getting some the multi-view images from the mesh. Then what we can see is that the only kind of some broken kind of the bridges across this kind of like different representation might be these two things. So basically, if we can convert the voxel representation into a mesh, and also we can convert the point cloud representation back to the implicit function, which means that we can basically convert like one to the other for any pair for the representations. So these kind of the conversions are basically the things that we are going to discuss in the today's lecture. And also one small kind of missing thing is that like given the multi-view images, how we can also convert this back to some geometry. So also the downside of the multi-view representation is that we are not basically having some explicit geometry information. We are basically converting everything into the 2D images, right? But would it be possible to also basically convert the multiple images into some geometric representation? Actually, that's what we are also going to discuss in the neural rendering part. So if using some the neural rendering the techniques, we can also convert the multiple images into the implicit representation. Then we can also do all kinds of the conversion, not only for the top 4 representations, but also for all the 5 representations. So we're gonna discuss all this kind of conversion idea now. So let's start with some kind of easier things. So we're gonna basically see the idea for the voxels to the mesh first, because this is like much easier. For the voxels to the mesh, basically what people typically use is this basically the idea which is called the marching cubes, which was actually first introduced in 1987. So it's basically more than 30 years old, the very old algorithm, but which is still kind of the standard technique for the voxel to mesh conversion. So here, the kind of problem that we are going to solve is that given a kind of the occupancy grid, where for each of the voxel, we have the information about like whether the voxel is inside or the outside the 3D shape, we are going to create a triangle in the mesh that basically approximates the surface. So how we are basically going to solve this problem? So even like, let's think about like the case that we are starting from the implicit function. So we are now having a function, the f here, which is basically indicating like whether each of the point is inside or not. So we're gonna get into the more details about this representation of the function. And let's start with the 2D case first. So in the 2D case, this algorithm is what's called the marching squares that will be basically extended for the 3D case, then it's called the marching cubes. So in this case, what we are going to do is that for each of the point in the 2D grid, we're going to first evaluate the function in a way to see like what are the points that are inside, what are the points that are the outside. So we are indicating the points inside as the minus the sign, and also the points outside as the plus sign. So we are basically doing some kind of the binary classification for each of the points, basically assigning all these like kind of the signs to the points. And then basically we're gonna see what are the edges of the boxes here. With that, we're gonna see basically some kind of the boundary of the shape. So basically, what we can see is that if we basically have some kind of the sign change between the 2 points of the end 2 points of the edge, that means that there will be some kind of intersection between the boundary of the shape and also the edge here, like this. So as you can see here, for basically this edge, if we have this edge, then we can see that the 2 endpoints are basically having the different signs. Then this basically means that the boundary of the shape and also this edge will basically have the intersection of the points. So basically, we are classifying all these kind of the points that are inside or the outside, and after that, we are also classifying the edges that will basically have some kind of the intersection of the points. And then what we are going to do is that we are basically connecting the intersection of the points in terms of basically creating some kind of edges of the boundary of the shape. And by connecting all this kind of the intersection of the points, we are getting basically the final of the shape. So that's basically very simple, the idea, right? So once we basically classify some of the edges that are basically having the intersection point, the way that we can find this intersection point is basically assuming that the implicit function is basically linear function over the edge like this. So basically, by just taking the 2 values at the end of the edge, we can directly find the intersection point by doing some kind of the linear interpolation. So then the next idea is that basically how we're gonna basically connect all the intersection of the points in a way to basically form the boundary of the shape. So for that, what we are going to do is that basically we are going to treat each cell independently. So we are basically not considering basically how we're gonna make this kind of the some connection of all the intersection of the points, but we are basically seeing each of the box independently here in a way to basically connecting all the intersection of the points. And then basically once we basically connect all the intersection of the points, the connection of all the intersection of the dots over the space will basically form some kind of the boundary of the shapes. So that's basically the basic idea, which is quite simple here. So here, basically, what we are going to say is that in the 2D case, let's see for each of the like single the box here, then we're gonna basically consider all the possible the combinations of the inside and the outside for each of the four corner points. The how many cases that we can see in terms of like having the combinations of the inside and the outside for the four corner points. If we consider all the possible the cases, how many cases can you see? Yeah, so we can see the 2 to the 4, the 16 cases, right? So then for each of the 16 cases, like we just need to make some kind of the lookup table in terms of like, how we're gonna make some kind of the intersection in the edges. So for example, in this case, let's say that the blue dot basically means so what is that? Yeah, let's say the blue dot was kind of the outside points, and the white dot basically indicates the inside points. For those kind of the cases, if we have like only one single the blue dot here, then we can consider connecting the two intersection points like this, right? So this will be the only the edge that we're gonna have in the boundary of this 3D shape, the 2D shapes in this case, right? And also we can basically connect these 2 points like this. And if we also have like 2 like blue dots here at the top and also the 2 white dots at the bottom, then we're gonna see some in the connection of the intersection points like this, right? So in this way, for all these 16D cases, we can basically consider making some kind of lookup table in terms of like, what are the kind of the edges that we're gonna see by connecting the intersection D points. So we're gonna see all these kind of the cases, for example, yeah. So those might be all kind of the cases. Actually, what we can even see is that like it turns out that while we are having the 2 to the 4 in terms of like the 16, all the possible the cases, you can see that the most of the cases are basically some kind of symmetric cases in terms of the rotation. For example, if you see the second case and the third case, you can see that the third one is kind of the rotation or some kind of the symmetric case of the second case, right? In this case, we have the edges like this, and this is kind of symmetric case, like having the edges like this, right? Also, if you see this case and this case, you can also see that these two are the cases of like just like the same case, basically like rotating one to the other, right? For those kind of two cases, we're gonna have the same edges like this, right? So instead of like making the lookup table for all the 16D cases, what we can do is that we can basically group all these kind of the cases that are basically equivariant after the kind of rotations. And then we're gonna basically see that there are very few number of the cases that we need to consider in terms of like making the lookup table. So if we basically group all these kind of some equivariant the kind of the cases after the rotation, for example, like these two are also equivariant cases, and also these two are basically some of the equivariant cases. So if we basically group all these kind of some sort of the equivariant cases, how many cases the groups that we're gonna see after like grouping all these kind of the cases? Can you guess? 6. Actually, also one thing we can do is that even we can group this and this. Because like, these are also the cases that we are having some of the rotation and flipping all the signs, right? So whether we have the 3 blue dots and the 1 white dot, and also having the 1 blue dot and the 3 white dots, actually these two will basically make form the same edges, right? So let's think about also this case and this case. For those two cases, basically these two are exactly the same, except for that now we are flipping all the signs, right? But however, we have the 1 blue dot and the 3 white dots, and the 1 white dot and 3 blue dots. We're gonna basically have these edge, right? So these will be basically exactly the same case. So if we also consider these two cases as kind of like equivariant cases, then after grouping all these kind of the cases, how many groups we get? Basically, we are basically getting the only like 4 groups like this. Yeah. So you can see that this is the case that all the 4 corner points are basically having the same sign. And this is the case that only 1 point is basically having the different sign. And this is the case that we are having the 2 different, basically having the 2 dots on the same side. and the other the two dots on the other side having the different designs. And these are basically the case that we are having the two dots having the same sign on the diagonal, and having the two dots having the different design at the diagonal, right? So those are basically the cases after grouping all these kind of the equivariant cases, which means that if we basically make some kind of lookup table for only these four cases, for every cell, basically we can apply the idea of like basically connecting the intersection of the points, given the basically the function values for each of the corner points. Does it make sense? Yeah, so basically these are basically the four cases that we will need to see in terms of like making all the possible the cases of like connecting the intersection of the points, and which is also quite obvious. So for the first case, obviously there is nothing that we can connect, right? There is no intersection of the point. In the second case, we're going to have the intersection point here and the other intersection point here. So we just need to make the edge like this. For the third case, we're going to make the intersection point here and the other intersection point here, which means that this is the edge. And the first case is kind of some sort of the programmatic case in terms of like we're going to have the four intersection of the point like this. Then how should we connect these four intersection of the point? Any answer for this? Well, yeah, let's just think about this. Well, actually, obviously, the problem for the first case is that there is no unique way to connecting the dots. Actually, we can consider these two cases, right? Yeah, as someone also mentioned in the Zoom chat, actually, we can consider these two cases. We can either consider like connecting like this, then we're going to have like one region like this and the other region like this. And also the other way around, we can connect the dots with the basically connecting like this, right? So we can consider like when you have the box like this might be the first case like this, or the other case like this, right? Which means that there are basically some ambiguous cases in this specific case. So for this kind of the case, what can be kind of the way to handle this kind of problem? Actually, there are some ways that we can basically handle this kind of the case. One kind of the good way to handle this case is basically subdividing the voxel into the smaller the boxes like this. And then we are also handling all these sub boxes independently. So we can try to basically handle this kind of the ambiguous cases by some kind of subdivision of the grid. So that's kind of the like one way. Yeah, and the other way around is that if we do not want to basically apply the subsampling, then we can just pick one of these kind of the two cases. So that's kind of some kind of the tricky solutions. So this is kind of the case for the 2D, and for the 3D, what can you do? For the 3D, actually, the idea is exactly the same, but now we are handling not the boxes, but handling the cubes. So that's the only difference. So also for the cubes, then how many kind of the possible combinations that we're gonna see of like basically assigning the plus and the minus sign for each of the corner points. So now we are having the 8 corner points, which means that now we're gonna see in total like the 256 the possible cases, like assigning all the signs for each of the 8 corner points. Then after that, we can also consider basically grouping all the equivariant cases, right? So after grouping all the equivariant cases, now we're gonna have basically 15 the groups, and also for each of the 15 groups, there will be kind of 6 cases that we're gonna see some kind of the ambiguities. For those kind of some ambiguities, we can also consider basically subsampling the grid, or basically just choosing one of the kind of the possible cases. So this is basically the very basic idea for the marching cubes and also the marching squares. And as you can see, this is really simple idea. You can basically very easily implement this idea. And also the good thing is that since we are treating all the voxel independently, this can be basically parallelized, which means that we can utilize the GPU for the fast implementation, so which is quite good. And also the good thing is that there are not much kind of some parameters here. The only parameter for this algorithm is basically the resolution of the grid. Other than that, actually, there's no the parameters for this kind of the algorithm, so which can be good in terms of that. We don't need to basically feed the parameters to get the best outputs. So which is kind of the like good thing for the idea of the matching cubes. But the downside for the matching cubes, as you can see, is that basically, there might be some kind of the kind of cases. For example, like if you want to recover some kind of the sharp edges of for example, like this kind of the box, depending on the kind of resolution and also the how we basically form the grid in the 2D or the 3D space, we may not be able to basically recover this kind of the sharp edges. So that can be basically one of the kind of the downside. And also there's no guarantee in terms of like getting some kind of specific topology of the shape. For example, like even in the case that when we want to basically get some kind of for example, like sphere-like the shapes, the output of the shapes can be not this pure topology of the shape, but it can be like some donut topology of the shape or something. So there's no guarantee in terms of like having some giving some topological structures. And also, yeah, there are so many kind of some downside for the matching cubes as well. But despite this kind of like this some sort of the downside, matching cube is still being used as kind of a standard technique to convert some of the voxel representation into the mesh like this. Any questions for the matching cubes? What is the function f typically used? Yeah, so we're gonna get into the point about like the implicit function later. In case like page 24, how much is something to be done in order to resolve the ambiguity? So that's the problem. For the subsampling, there is no guarantee that subsampling will really resolve the ambiguity issue. So that's basically why we basically need to set some kind of threshold in terms like how many times we're gonna try the subsampling. And after like iterating all the subsamplings till we see some ambiguity in the cases, then the only solution that we can take is basically just picking one of the ambiguous cases. So that can be kind of the downside of the merchant cube algorithm. The definitions of the equivariance. Yeah, so basically, we can consider like what are basically the same cases that we're gonna see the same kind of the connections of the intersection of the points. For this kind of example, for example, like for all the rotation and the symmetry cases, like for this and this, like you can see that these are basically just symmetric decays, right? So you can basically see that you can first like connect these two intersection points and just flip this edge, then you're gonna see the same outputs. And this is also kind of the case with the rotation. Let me see. Yeah, those kind of the other case. Yeah, this is also another case with the rotation, right? And also the other case is that if we also flip the signs for all the four corner points, for example, for this, if we just flip the signs of all the corner points like this, we are basically interested only for the kind of the cases of like having the edges with the sign changes, right? So when you basically flip the signs of all the corner points, you're gonna also see the same intersection, the connection of the intersection points like this, right? So these two are also equivariant cases, right? And also the rotation and the symmetry of like this case will be also another the equivariance cases, right? And so these are so this and this and this and these for the were the equivariant cases. And also this is the equivariant case because it's the case of like flipping the signs. And also the rotation like this will be this. And what else? This and this. Yeah, these are all the equivariant cases, right? Because these can be basically converted one to the other by flipping all the corner points for the flipping the signs of all the corner points, or by rotating or just flipping the boxes. So these are basically the cases of like grouping all the equivariant cases. Does it answer your question? Well, I mean, the continuity is about the function, not for the grouping the equivariant cases. Any other questions? What is the potential downside to guessing as opposed to substituting? Well, I mean, actually, as you basically subsample and the more, you will be able to get some better the outputs. The only downside for the subsampling would be is that it will just take some more time, right? So if you basically, and also as you basically apply the subsampling and the more, it will be more difficult to parallelize all the process. So that will be kind of like main downside for the subsampling. Any other questions?
My question is mostly on how is one of those with the blue dots. So if you have one blue dot and three blue dots, how are those two equivariant to each other? What is the map? What is the function that we use to make them equivariant? Like you split, you said something like splitting, which is something I've never seen in equivariant maps. It's usually the reflection or rotation.
Well, I mean, the equivariance here that I mean is basically just finding some of the cases out of this kind of like 16 the discrete cases in terms of like what are the cases that we're gonna basically form the same edges like this, the edges of the connecting the intersection the points.
So it's more like combinatorics rather than group theory, because equivariance is mostly used in group theory. That's why I'm a bit baffled.
Well, I mean, these are basically the way that we are defining the equivariance. Basically,
so what's a definition of equivariance for this?
Yeah.
What would be the definition of equivariance? Because equivariance is from group theory, from what I know.
Well, I mean,
and you need a symmetry
group theory, we can define like the equivariance as we want. So the way that we are defining the equivariance here is basically when you basically have the connection of the intersection the points. So given this like the edges here and the 4 edges here, these would be the two cases that we are having the connection of the two intersection the points like this, right? So this is the case that we are saying that these two are basically equivariant the cases in terms of like having the same set of the connection of the intersection the points. There's nothing basically special here.
Okay. I don't get it, but okay.
So yeah, so let me move on. So actually the thing is that we can apply the same idea not only for the squares and the cubes, and also there's the case like applying this idea to the tetrahedra as well. I mean, there are also obviously the other ways to apply the same idea into any kind of some sort of the volume representation. So actually the thing is that the funny thing is that the reason why people just came up with this idea of the marching tetrahedra is that the marching cubes was patented for a long time. So people could not use this idea for a long time. So that was the main reason that people just wanted to introduce like the new method so that they can basically use the idea, like the patent-free way. So this is also the same thing, but not basically having the cube, but basically having the independent the tetrahedron in a way to basically connecting some of the intersection points as well. So for these kind of cases, you can also see that there are basically also the 4 corner points, which means that there will be 8 for the 8 possible cases. And then you can basically also connect all the intersection of the points in terms of building all the edges of the mesh. And also the good thing of the marching the tetrahedra is that now there is no ambiguous cases. So we can basically have all the kind of like the cases basically without basically trying any kind of like subsampling or something. So that's kind of the advantage of the marching tetrahedra. If you also see some kind of the very recent papers about like some 3D reconstruction and the 3D generation, you'll be able to see that actually this idea of like marching the cubes and the marching tetrahedra is widely used in many kind of the cases. And I just like prepared this slide to basically provide some kind of example for that in terms of like, this was kind of the paper, which was basically utilizing both the implicit representation and also the marching tetrahedra based kind of mesh representation in terms of getting some kind of some accurate the 3D the generation or the reconstruction the results. So what they do is that they basically first try to reconstruct the 3D shape by getting the implicit function over the 3D space. And what they do is that they are basically reconstructing the final mesh using the marching the tetrahedra. and also deforming each of the point over the 3D grid in a way to refine the final shape, refine the final demesh. So this was kind of also the example of like, making some sort of the hybrid version of the representation, combining some implicit representation and also the explicit, the tetrahedra, the grid representation, in a way to get the accurate the 3D the outputs in the some kind of the reconstruction the tasks. So this was kind of the example of utilizing this kind of like marching tetrahedra the idea in the neural net the prediction. So we can also get into this idea later. Any questions before we move on to the other deconversion? So this was basically a very simple idea in terms of converting the voxels into the mesh. But the conversion from the point cloud to the implicit function is slightly more complicated. So we won't have the time to discuss all the details about like this conversion, but we're gonna get into some of the basic idea that how we can do this without the neural net. And also the thing is that for those kind of the conversions, like people typically consider think we might need to have some kind of some neural network for the conversion. But actually what we are going to discuss in this lecture is that actually we will see that without the neural net, actually we can directly convert the point cloud into the implicit function. So this is not a problem that we need to have some kind of some prediction. Without the prediction, we can directly estimate the implicit function from the given the point cloud. But also the thing is that if we can leverage some kind of some prediction power the neural net, then we can actually do some better job. So actually we're gonna get into the point later. So basically, to do some kind of conversion from the point cloud into the implicit function, actually the thing is that we need to have some, not only the points in the point cloud, actually we also need to have the surface normal information. So actually the surface normal information for each of the point is the essential information to recover the surface and the volume information. So actually the way that we can formally define the surface normal is basically like this. So we basically need to first define the tangent plane. So how we define the tangent plane? So actually I just skip some of some mathematical details here. But the way that we can define the tangent plane formally is like in a slightly more mathematical way is that for each of the point, given any point over given the surface S, if we also think about some of the curves that are basically over the surface and also passing that point, so we can basically draw infinite number of the curves that are basically passing this point P over the surface. Then we can actually consider the tangent line for each of the curves. Right? So if we basically draw all the basically some kind of the curves that are passing the P over the surface, then we can basically also compute the tangent line for each of the curves at the point P as well. Then for most of the cases, not all the cases, but for the most of the cases, we can basically consider finding this kind of the plane that basically includes all the tangent lines of the curves that are passing the point P. So this is basically the definition of the tangent plane. So if we basically consider any kind of point P over the surface and basically draw any kind of random the curves passing over the point P, and then we basically compute the tangent direction for each of the curves passing the point P, then we can find the plane P like this, which is basically including all the tangent directions. So this is basically the formal way to define the tangent plane. Then given this kind of the tangent plane, the surface normal is actually defined as the normal of this kind of tangent plane. So if we basically have the tangent plane, the unit vector, which is the perpendicular to the tangent plane, become the surface normal. So that's basically slightly more the mathematical way to define the surface normal given the point cloud. So then basically the question is that when we only have a set of the points, so when we have the point cloud without any kind of the surface information, how we can try to estimate this kind of the surface normal information? Do you have any idea for that? How do you define the tangent equation from the multiple tangent line? Well, yeah. So there are basically some kind of so basically what you can do is that technically you can, if you draw any kind of the two tangent lines, if you can basically compute basically the tangent vectors for each of the curves, then if you take the cross product of these two vectors, that will be the surface normal, right? And also this normal direction will define the plane. And this is also the case that when these two tangent vectors are basically independent of each other. So for most of the cases, basically we can define the tangent plane like this. But obviously for the cases that we are having the sharp edges like this, so we have this kind of the surface having the sharp edges like this. On this point, if you basically find the tangent plane like this, then you cannot basically find the tangent plane. So this is kind of the degenerated case. But except for this kind of like degenerated cases, if we have some regular surface that we can basically define the tangent plane like this, then you just need to take the two curves and take the tangent vectors of those two curves, and then the cross product of these two vectors will define the normal direction. So that's the kind of the basic idea. It's like curves from the right points. And so here basically the idea is that how we can basically compute the surface normal given a set of the points. So that is kind of the main question. So actually there are multiple ways that we can do this, but the simplest way is that we are basically locally approximating the local region of the points as the flat plane. So given any kind of like the set of the points, we can consider basically approximating some local region at this point with the flat plane. Then we can just directly take the normal of the plane as our basically the surface normal. So that's basically the basic idea. Obviously, that may not be basically that accurate, but that can be the simplest way that we can basically estimate the normal of the point cloud. And also the kind of the issue here might be is that there will be basically two ways that we can define the surface normal. So basically we can take this vector or the opposite vector as well, right? Which means that if we basically compute the surface normal over the point cloud, we can see some kind of cases that like one point having the normal direction like this, and the point next to this one basically having the normal direction like this, right? Which may not be good for the many of the cases that we're gonna see. What sort of the issues we're gonna see. For those kind of the cases, we can also consider having some sort of the post-process step in terms of like aligning all the surface normal directions, like the consistent way across all the points, in a way to basically flip this normal direction into like this. So this can be like another step that we need to do in terms of like making all the normal directions over the point clouds to become like more consistent. Obviously, we don't need to basically approximate the local region with the flat plane. We can consider basically approximating the local region with some kind of the multivariate polynomial of the function. So we are basically not taking the linear approximation, but basically having some sort of the polynomial approximation over the shape. Then basically given the polynomial of the function, we can also compute the normal direction from the function. And also one thing that I also wanted to say here is that here at this point, we can also think about like utilize some kind of the neural net, basically utilize some kind of the prediction power of the neural net in terms of like getting some better accuracy in the normals. Because here the problem might be is that the issue in terms of like either fitting the plane or some kind of the polynomial the function is that the output will be basically sensitive in terms of like how many kind of the neighbor points that we are taking, right? So basically to this kind of like to do some kind of like fitting of the planes or some polynomial the function over the point cloud, we will need to basically take some kind of some neighbor points over the point cloud. And also we might need to basically consider adding some kind of the weights for each of the points, right? So that can be basically the basic idea for this kind of like fitting. But depending on the region that we are taking some neighbor of the points, and depending on how we give some kind of the weights for each of the points, actually the output of the fitting can be changed a lot. So that's kind of the problem of this kind of the idea. So what we can do is that there's also kind of the work which is basically utilizing the neural net, not to directly predict the normal direction, but actually to predict some kind of the point-wise the weights in terms of like getting some kind of the better fitting the accuracy. So here the basic idea is that instead of like directly just like estimating predicting normal direction for each of the point, for each of the case that we are fitting the plane or some kind of the polynomial function, now we are basically predicting the weights to get some kind of the better quality of the fitting. and also in a way that we can get some kind of better the output of the normals from the not from the prediction of the normal direction, but from the prediction of the pointwise the weights in terms of like in this like the fitting process. Then since we are basically utilizing this kind of like the fitting processes as well, compared to the case of like directly predicting the normal direction, actually predicting the pointwise the weights can actually achieve some way better accuracy in the surface normal estimation. So that's kind of the interesting the idea in terms of like combining the prediction power of the neural network and also some kind of some fitting idea, some classical idea in terms of like getting the normal information. So that's kind of the one thing. But basically, like given this kind of like the surface normal information, what we are going to do is that we are basically going to recover the implicit function. And also, so basically, how we can also define the implicit function? So implicit function idea is quite general idea in terms of like representing the 3D shape as the function. But actually, there can be some multiple ways that we can define the implicit function for the 3D shape. Actually, one simple idea to define the implicit function is to define the occupancy, right? So we can consider having some kind of the binary function. So given any kind of query point in the x, for example, we can basically make out the function in a way that the output of the function becomes like 0 for the like inside, and also make the 1 for the outside, right? Well, we can flip this too. We can make the inside to be 1 and the outside to be 0, whatever. So basically having this kind of the binary value is basically one of the way to define the implicit function for this 3D shape. So basically encoding some kind of the occupancy information using the function, right? And here, this is another the idea in terms of like defining the implicit function, basically encoding some signed distance. So here the basic idea is that given any kind of the point in the 3D space, now we are encoding not the occupancy, but actually the distance from the point to the surface. So for any point over the 3D space or the 2D space, we can consider basically encoding the distance from the query point to the surface of the 3D shape. But the only thing is that we are basically adding the sign in terms of, this is the example that we are basically adding the minus sign for the points inside of the shape, and basically having the plus sign for the points of the outside of the 3D shape. In a way, so these are basically the case that we are encoding the sign, the distance. So we are encoding the positive the distance for the points on the outside, or encoding some negative distance for the points on the inside. And obviously we can basically flip the sign. It does not make any kind of like the difference. And then once we basically have this kind of the implicit function, then we can basically find the boundary of the shapes in a way to basically recover the cases of the like having the basically having the set of the points which are basically getting the output of the 0, right? So if we basically take all the points which output of the function becomes 0, and the set of these points will basically form the boundary of this 3D shape. So basically that will be the case that we are basically recovering the surface of these 3D shapes. What does mean the positive distance between the point and the surface? So basically we are basically measuring the distance from the point, any kind of the query point in the 2D or 3D space to the boundary of these 3D shapes, right? But the only thing is that for the points the outside, we are basically having the positive sign. And for the points inside, we are basically giving the minus sign. So this is the case that now we are having the, not just kind of the distance, but the signed distance, which is basically having the information of the distance plus the inside and the outside information. Just empty space. What is the meaning of the question? Yeah, empty space, basically, yeah. For the empty space, basically for the points, the space outside of the shape, we are giving the positive sign, or the region occupied by the 3D shapes, we are giving the minus sign. Does it make sense? Or we can just flip the sign. We can actually give some positive sign for the inside and the minus sign for the outside. That's not make any kind of difference. Yeah, so this is kind of like one way that we can basically define some kind of implicit function for some either 2D or the 3D shapes. Then let's think about the case that we are having a kind of a set of the points. If we have the set of the points, and if we also have the surface normal information like this. And let's assume that also the normal information, the surface normal for each of the points are consistent to each other in terms of like having the consistent orientation. Like for example, like all the normals are basically heading the outside of the shape. So we want to basically recover the shape like this, right? So given this kind of like a set of the points with the normal information, by the way, the case that we are having the point cloud with the surface normal information is the case that we are having the oriented point cloud. Oriented point cloud. So when you have this kind of like the oriented point cloud, then how we can basically define this kind of the signed distance function, given any kind of the query point in the space. If we have a set of the points like this and the surface normal information, how we can basically compute the signed distance for any kind of arbitrary point in the space. So that's basically what we are going to do, right? Do you have any idea for this? Any simple idea in terms of like the curve, compute the signed distance for the query point? This is the quiz question. Any idea? So let's think about the case that we are having a set of the points like this. Let's assume that now we have the surface normal information like this. And for any kind of the query point, how are we gonna basically compute the signed distance from this query point to given the set of the oriented points? Yeah, some people posted on the Zoom chat. Actually, we're gonna discuss mainly three ideas in terms of like how we're gonna do this. But the simplest way is actually, as you can easily guess, it's nothing but basically from the any kind of query point. We can just consider find the closest point from the query point to the any of the points in the point cloud. Then we can basically approximate the local region of the point cloud as kind of the flat plane like this. Then we can directly compute the distance, the projection distance from the query point, this plane, right? So this is the simplest idea in terms of like computing the signed distance for any kind of the query point. Makes sense? For any kind of query point, we are finding the nearest point, approximating the local region as the flat plane, and basically, measure the distance from the query point to this kind of the tangent plane. So that's kind of the easiest way that we can basically solve this problem. Obviously, the downside of like this idea is that we are basically approximating the signed distance with only one the closest point. So that's kind of the downside of like this idea. So what we can do is that we can consider basically extending this idea in a way to not only considering a single point in the query in the given the point cloud, but actually considering some multiple the points with some kind of the weights. So at the end, what we are going to say is that we can consider basically taking some weighted sum, weighted average actually of this kind of the signed distance from the multiple the points. And that's also the idea which is called the moving least squares. But actually, we're gonna briefly see some kind of the interpretation of like this idea based on the local corner regression things. So this is basically what we are going to do, right? It's a very general idea. So we've given any kind of sample the points where we know that the output of the function becomes 0. So we are basically want to basically approximate the whole the function fx, right? So this is basically the very general problem that we are going to solve, right? For any kind of given a set of the points, either in the 2D space or the 3D space, where we know that the output of the function should become 0, we are basically approximating the entire the function over some continuous space. So that's basically what we are going to do. So if we basically recall the idea of the Taylor expansion, then what we can see is that the function value for each of the point in the point cloud can be basically approximated like this, right? Can be basically rewritten as the Taylor expansion like this. And if we take the first order series, then we're gonna basically have this formulation. So basically here, what we can see is that this is basically the value that we know that this should be basically 0, right? So any kind of the point in the given the point cloud, we want to approximate the output of the function that we know that this should be 0, right? And this can be basically rewritten like this. And actually the thing is that, so this is kind of the formulation for any kind of the arbitrary some closed points x, which is actually our the quarry point. So given any kind some sort of the points which is close to the the pi here in the point cloud, we can basically approximate the function value at the pi like this using the value at the quarry point. Actually, the thing is that we know that this value should be 0. And actually, we want to basically approximate this. We want to basically calculate this, right? So let's denote this fx as the y here. So at the end, what we want to do is that we want to basically get the y. And we know that this should become 0, right? Makes sense. And then the only kind of the missing information here is that we also need to get the gradient at the function at the point x as well. And we also don't have this information. So what we want to do is that we also want to approximate this because we cannot get this information. So the only way that we can basically approximate this information is also to basically approximate the first derivative, the gradient of the function at the point pi in the same way. But now we are taking the 0 order, basically the approximation, basically, which means that we are taking the gradient at the pi as the gradient of the quarry point x, which is really bad approximation, but this is the only actual way that we can do some kind of like guessing some information of the gradient at this point, right? So this is basically what we are going to do. And also what we can see is that the gradient of the implicit function at the point P actually becomes the numeral directions, right? So in the case that when you have the surface numeral information for each of the point, this is basically the case that we are basically getting the gradient of the implicit function at the point pi, right? So basically we are assuming that when you have the surface numeral information, now we are having the first derivative information of the implicit function at each of the point in the point cloud, and we want to basically approximate the gradient at the quarry point as kind of the gradient of the function at the closest point in the given point cloud, right? So this is basically the basic interpretation. Then what we can do is that we can basically plug in all the things in terms like minimizing this difference. So basically, this is basically the formulation that we have seen in this slide. So we know that these should be exactly the same. So we basically want to minimize the difference between this and this, the left-hand side and the right-hand side. So this is what we get here. So we basically want to minimize these two differences while basically having some kind of the weights for each of the point. So now we are considering not only a single point, but all the points that we are having in the given the point cloud, while minimizing these two differences, right? And what we know is that the value for this should be 0, right? And then we are also approximating the gradient of the implicit function at the point x as this, the gradient of the function at the close point, the pi, which is the things that we know as kind of the surface numeral information, right? Then what we end up getting is basically this. So we basically want to find the best value of the y here, which is basically minimizing this, while basically having some kind of the weight function for each of the point. Obviously, we're going to define the weight for each of the points based on the proximity from the quarry point to each of the point in the point cloud, right? So what we can, so if we basically rewrite everything, then what we end up getting is basically this. So this is basically the solution of the least square problem in the previous slide. So you can see that now I basically flipped the order like these two, like this. Okay. So this becomes the final solution. So as you can see, what we are seeing here is that this is basically nothing, but basically we are computing some kind of defined distance for each of the point. But now we are not only taking the closest point, but we are taking all the points in the given the point cloud while having some kind of the weights for each of the point. So you can see that this is actually turns out that it becomes nothing but basically taking some sort of the weighted average of this design distance for the multiple points in the given point cloud. So now the output becomes like something like this, and also it basically we get some kind of results depending on the weight function that we are defining. So we can basically define the weight function as we want, but actually we can basically define the weight function like this. Basically, as we have basically some closer points in the space. Okay, we are basically increasing the weights. And as we basically, as we basically have the query points, the point in the point cloud, which is closer to the query point, we are increasing the weight. And as the point in the point cloud becomes farther from the query point, we are basically decreasing the weight, right? We can basically simply define this kind of the weighted sum of design distance, which will be slightly better than just taking the one closest point in terms like measuring design distance. And also this is basically quite simple idea that we will be able to very easy to implement, and also it will be quite fast. But also the thing is that still this is kind of the approximation, not using the entire points, but only with some kind of the local region, because we're gonna obviously give some higher weights for the local region. And also depending on the weight function that we're gonna have, the output might also vary a lot. So that's kind of the downside of this kind of the idea. So that's the basic idea for the moving all these squares. So that's why basically also people came up with the idea of like doing some kind of the global optimization. So before we move on to the next idea, do you have any questions on this? Why is it important to consider relative quantity inside the mass of the surface? Is there a version of a unversion of the sign distance or unsigned version? Well, yeah, I mean, we can obviously also consider some kind of the unsigned distance function as well. So it's kind of the doable. Actually, the good thing of the sign distance function is that we can basically have some kind of some continuous function. So basically, if you have the unsigned distance function, that means that like the distance becomes here the positive, and as you get closer to the boundary of the surface, the distance will become 0, and then it's kind of like going up to the plus as well, right? So we're gonna basically have some kind of the some value like this. So if we basically see some kind of the distance along this line, it will be like this, having the positive distance and 0, and then positive again, right? So this is not the case. I mean, obviously this is like continuous function, but it's not basically the smooth function in terms of that we are having this kind of the minimum where it becomes basically 0, right? For those kind of cases, especially for the next idea that we're gonna see, if we have this kind of the unsmooth kind of the function, it's hard to recover the final the unsigned distance. So that's also why typically we also use the signed distance, the distance function. And obviously the good thing of the signed distance function is that we can basically provide information about not only the distance, but also the inside and the outside of the shapes, right? So when you basically query any kind of the points, if you only have the the distance information, then you don't know whether this point is really inside or the outside, right? So it does not actually give any kind of the volume information, only the information about the distance to the surface. But if you also provide the signed distance, and then depending on the sign, you can immediately see whether the point is inside or the outside, right? Which is giving some more like direct the volume information for the shapes, which can be useful in many kind of applications. Any other questions on this? Any other questions? Okay, so actually the next idea is about the global optimization, which is like the most important part in this lecture, but we only have the 4 minutes. So let me briefly just like introduce the idea, and I guess we will need to continue in the next time. So this is basically the idea which is called the Poisson the surface reconstruction, and we're gonna get into the point of like why this idea is called the Poisson the surface reconstruction, which was also introduced in the 2006. So it is quite old idea, like almost like 20 years old. But still, like this idea is still being used as kind of the some standard technique for the conversion from the point cloud into the implicit function. And also one interesting is that the author of this paper also says that this idea also has been used to reconstruct the Martian landscape from some kind of some scanning data. So you can see that actually this idea is really has been widely used in many of the lots of the applications. So if we actually basically see the basic idea here is that what we have seen in the previous slide is that actually the surface normal information is providing some kind of information about the implicit function in a way that the gradient of the implicit function, the sign distance function, actually becomes the surface normal for the points, right? So this is kind of like basic idea. When you have a set of the sample points over the space, along with some kind of a surface normal information, then what we get is that actually we are getting the information about the information about the implicit function at these points. Not only the information about the function itself, but as actually the information about the gradient as well. So when we basically have the surface normal information, we know that for each of the points over the point cloud, if we take the gradient of the implicit function, this should be basically the normal direction that we are having, right? So here the basic idea is that if we have some kind of the gradient information for the function, given this information, how can it recover the original function? So this is basically what we are going to do. So more formally, when you have some kind of some vector field, which is the first derivative of the given function, given this like vector field information, actually we want to recover the original function. So that's basically the problem that we are going to solve. So if we can somehow take the integral of the given vector field, the integral of this vector field should become the original function, right? But here the question is that if we take any arbitrary vector field, then would this vector field will be integrable or not? Is there anyone the answer for this? If you took the vector calculus course in the first year, then you should know this answer. Anyone who recall the things that you learned in the vector calculus course? Actually, the thing is that for most of the cases, the arbitrary vector field is not integrable because there's some very specific condition for the integrable vector field. So actually, the vector field becomes like integrable when basically it becomes the conservative vector field, the conservative vector field that satisfies all these conditions like this. So only for this kind of some special cases, we can see that the vector field becomes integrable. Then we can directly compute this, directly recovering the function f like this. But for most of the cases, we're gonna get the surface normal information, which is not integrable, which means that we need to basically solve some kind of the least squared problems in terms of like we are finding a function f, which integral at each of the point becomes the given the surface normal information. So basically, we are going to solve this problem. And in the 1D case, because basically we are getting this kind of the formulation. See, so we are basically finding a function f, which first derivative becomes the given the output of the given the input function, right? So the Poisson the equation is basically whole the idea like solving this problem. So if I just like go ahead with a couple of more slides. So let me just skip some details here. Basically, what we can see is that let's just see the 1D case. The simple is the 1D case. In the 1D case, basically, if we find the solution of this equation, then the equation basically becomes like finding this case. Basically, finding a function f, which is second derivative, becomes the same with the first derivative of the given the function. So if we basically find the solution of like this case, finding a function f, which the first derivative becomes the same with the input function, the solution of like this equation actually becomes this case. Finding a function which in the second derivative becomes the same with the first derivative of the given the function. And this is the case for the 1D. And for the in the higher dimension of the space, what we can get is that given any kind of the vector field, if we find a function f, which Laplacian becomes the same with the divergence of the vector field, then that's basically the solution that we are finding, minimizing the difference between the derivative, the gradient of the given the function with the given the vector field. So this is basically what we are going to do. We are going to solve this equation. So given the Laplacian operator and the divergence operator, we can, if we have some kind of input the vector field, which is the surface normal information, we are basically finding the function f, which becomes the solution of like this equation. And this equation is called the Poisson's equation that you can see in many kinds of some physics problems. And that's why this technique is called the Poisson surface reconstruction. So we are going to briefly go over with some more details the next time on the Wednesday. And after we basically finish to discuss all the idea for the conversion, we are going to get into the idea about some more like tangible, some neural net architectures that can process this 3D data. So let's stop here. Any questions for some conversion, any ideas that we discussed today? In the DM-TED, how can you find the points in 3D? So actually, yeah, there are two types of the points. So we are basically having the tetrahedra structure. So let me go back to this one. Yeah. So here, as you can see, we are having this kind of like the points for the tetrahedral structure. So once you have this kind of like some tetrahedral structure, from that, using the marching tetrahedral idea, you can basically recover the mesh like this. So you can see that the red line here basically shows some kind of the mesh in the 2D space, and the red dots here are basically showing some kind of the dots of the tetrahedral structure. So what we do is that here, basically you can first recover the shape by predicting the implicit function. And if you basically want to define the given the implicit function, then you can also move the red dots here in a way to basically deforming the tetrahedral structure. Then you're gonna also get the see some kind of deformation for the final mesh as well. So that's kind of the basic idea here. Can SDF have a self-intersection? Self-intersection of the what do you mean by like self-intersection? Like number 8.
I think he means the shape of 8, not slide 8.
Oh. Like this? Well, I mean, it's possible, I guess. Yeah, obviously you can, but this is just like the case that you're having the two kind of some shapes that are having like one contacting points, right? Yeah, obviously we can define the sign distance function like this, having the two shapes like this that are basically having one contacting point. Well, actually, I couldn't get the point. Actually, we're gonna get the zero level set like this. And the distance in here will becomes the minus, and the sign distance here also becomes the minus. Having the zero level set like this. I don't know whether I answered your question. Any other questions? Okay, so if there is no more questions, I'm going to see you on Wednesday, and we're going to continue discussing the Poisson surface reconstruction. Okay. Bye.